Okay, welcome back, not just to this class, but to school. It is really nice to be able to see people's faces. I love this camera, but I don't love it that much. It is not nearly as nice as actually being able to talk to you person to person. Guess I don't have to do really a lot of introductions. All of you know who I am, I assume. If you forgot who I am, I gave you an introduction video last week where I told you you already know who I am. So, last week, what did we cover? What's that?
Truth tables.
Truth tables?
Binary.
Tables.
K-maps.
Ooh, yes.
Grade code.
Okay, and all of this is just fun, informative, little knickknacks that are foundational to computer and integrated circuit workings. Really, most circuits consist of a series of amplifiers, resistors, comparators, just simple components that are all connected together. Integrated chips, these little black silicon things that you get in electronics. So I brought this in. If you can guess what this is, I'll give you $1 million. Huh? Hold on, let me go extract my $1 million. Integrated chips like this one, which you can walk around, and it's basically just a tiny black piece. Inside of here are a bunch of different gates, or a bunch of different, there sometimes are resistances that are built into it, but you guys can just pass that around. It's the little chips themselves are just giant series of digital systems that just use digital Boolean algebra. That's all it is. Every once in a while you'll have one of them fail, which is why your program will crash or something. But that's all this is it's just a series of these tiny components where you have nanoscale Boolean algebra being performed. Something to the point where the actual pockets inside of the silicon components, or inside of whatever comprises them, tend to be really close to the size of electrons. This is how advanced our computing has become. So when it comes to understanding this is the foundations of computer electronics. None of you will probably ever need to know this. So why am I teaching it to you? So let's talk about what we're going to be talking about this week. Oh, the magnet came off. Okay, now I give all of you guys a reading assignment for this week. It's not due till today because I didn't think it was right to have you hand in an assignment when we were all supposed to meet each other and then we didn't. Plus, as I sent you in the announcement, don't work on homework assignments on snow days, because I should, one of the moral quandaries that every professor is going to have this semester is, how do we handle having random days off during the semester? That's not going to be easy to address, because how is it how do I give you like, okay, homework is due, but this is one of your spring break days. It's gonna be a challenge. So on days when you have spring break days, I will be assigning less homework, but I will not be assigning no homework unless you kids get to a point, or I get to a point where one of us is just not doing something right. But I will assign less homework on those days. The goal is, I don't want to murder you. You're all students. That's important. So, okay. What I gave you for a reading assignment, though, for those of you who may have done it, is we have to talk. This class is a top-level class in electrical circuit design. This is what, this is Doan's biggest course in electrical engineering and in computer design as a whole. So really I see this as a design class. And this is something where I love designing stuff. I love making stuff. So if you don't like designing things or making stuff, I'm sorry, but we're going to be designing things, making stuff, because it enhances your ability to understand the circuits around you and the processes that are going on. Plus, it's a great way to engage a lot of other material. For those of you who have taken 350, everything is an input and an output. It's all about system flows. We'll talk a little bit today about how it relates to 350 materials. A lot of electronics are being used heavily in control systems because of their capabilities to both sense and issue commands. Pretty much any system, hydraulic, pneumatic, thermal system, can be directly integrated into an electrical system. There are thermal, there are thermal materials where if you run power through them, they suck heat from one side and draw it to the other. Joel Tremont actually did some work with those. There are electrical devices that power motors. A lot of motors are electric now. They have been highly refined. Now you get about 60% efficiency out of a motor, but that's a different story. Still higher efficiency than out of like gas-powered motors. But electric circuits integrate well with just about every component, every different kind of system, which is why control systems and electronics are very much hand in hand. If you understand electronics, you can usually understand control systems really well, at least modern control systems. So when it comes to design, all of you took 210 with me. So, this marker's going to decide to die. I think I've been holding it up for too long. When it comes to design, there are 4 major steps to design. Step 1 is problem framing. This is understanding what you need your system to do that you're developing. Okay. Step 2 is ideation. This is putting together different concepts, locating things that do stuff, finding components, identifying individual pieces that will help solve the problem. 3 is realization, involves construction. And 4 is analysis. Okay? I've taught all of this to you. This isn't new. But the concepts are slightly different when it comes to electrical engineering. What does problem framing look like? Well, it looks the same. You do some research. Depending on the type of project you're doing, you may go in and you may need to really look heavily at a certain industry. Let's say you're designing a GPS unit. Okay, if you don't have any experience with GPS, you're probably going to go look at how does GPS work. And that will help you understand the problem framing. You just, hey, I need a GPS unit because I want to know where I am. that gets a little bit more challenging. So problem framing involves a lot of background research to understand the problem, but it also understands why are you designing this. If you're just making a GPS for yourself, that's great. It can be terrible. You can shock yourself, go crazy. If you're designing this for somebody else, though, there are a number of considerations you have to take in an electric circuit. Chapter 1 was like twice as long as the reading assignment I gave you guys because it was just massive. I was going to try to get through it all in 1 week, but to cover all of that reading material, I didn't feel right giving you 50, 60 pages to read. And all of it was good. It was all good content that's applicable in this class. But everything that is in chapter 1 of the textbook this week exists as a sub-piece of problem framing. Okay? In problem framing, you perform the following tasks. You understand the population. That's step 1. 2 is where you recognize constraints / functional requirements. For example, if I were to give you a truth table, and I say, hey, build a digital circuit that does this. That truth table is a functional requirement. It's do this. Whereas your constraint may be, it has to be on a 5-volt system. It can only have a maximum of 100 milliamps running through the circuit or drawn from the power, or it can only be a 5 milliwatt system. That could be a constraint that's on the system. Constraints can be pretty legit. I guess I'll jump back into this when we talk about how to correlate this all to electronics. Third step was measures of quality. Fourth step is existing technology. What is already out there that solves the problem? You need to know that no matter what you're designing. Don't ever reinvent the wheel. Unless you feel like you can build a better wheel, which, have any of you guys seen the US military created a bunch of airless wheels? They're just like flexible tracks. They invented a better wheel. They reinvented the wheel. And the fifth is make the decision of whether or not to design. That is critical. Okay? Just because you want to design something doesn't mean you should. Now that said, if you're going to take it as an approach of I want to learn something, yes, you can design something for the sake of learning any day. That's great. So go ahead and learn. Go ahead and gain that knowledge, okay? But if you're designing something for functionality, bless you. If you're designing something, dang it, I'm gonna have to learn both of your guys' names again. No!
See if it takes full semester like last time.
It did take all semester. This is my nightmare. Now, if 3 of you show up to class on Friday, I'm leaving. So it is important to understand whether or not you should design. And whether or not you should design really comes down to these 2 steps right here. What makes a good system, and does the existing technology fit that system? Now for this class, your semester-long project is to develop an IoT sensor. I can tell you right now that if you find an IoT sensor that hasn't already been made, I'm gonna throw money at you, let's build this, okay? Because there are great minds who have been working on IoT for about 15 years. maybe even a little bit longer, but IoT has really only been relevant the last 15 years. If you can come up with something that is innovative that nobody else has thought of, there's potential for it. I can tell you that anybody is looking, if you can find a way to make any system smarter, it's glorious. But I'm having you build IoT systems not because I want you to go through the process of, is this going to be better than something else? I don't want you to put that expectations on you, but I do want you to learn. So we are going to be doing design process in this class for the sake of learning. But in real life, you would need to ask this question of whether or not you can build a better system. Now, that said, there are so many systems out there that can be improved. There are many systems out there that right now, you sitting in this classroom could design something better. I know that for a fact because I've seen college students build and patent stuff. It's not because they were brilliant, it was because they just recognized there was a potential for design. Okay, a lot of the brilliant innovations that have happened the last 40 years have come out of kids that were in college or dropped out of college who recognized a design potential and they just took it. So, yeah, so this is the process, and really we're going to be focusing on this right now because that's kind of the topic of the book. What the book focused a lot on was the 5 principles of 5, I don't remember what they called it. There were basically 5 measures of quality that identify what they are. So the 5 measures of quality, we're talking about cost, why is cost a measure of quality? Yeah. This is going to cost $3 bajillion to build or purchase. You have to be able to make it. You have to be able to afford it. Okay, we live in a society where the exchange of goods and services is highly regulated, and it's something where if you cannot give this to somebody because there is no way to exchange it for an appropriate amount, if it's not worth what it does, at the end of the day, nobody's going to purchase it, and it's not going to be a worthwhile solution. Money is a factor in every design process, and it's not something that we will ever get away with because we live in a society where it involves the exchange of goods and services. Okay? So, money was one. The second one was power. Okay? When it comes down to it, power and cost are fairly related. Not just because energy costs money, but because energy is itself a form of currency. All of us utilize energy in many different forms. Food is a form of energy that is a currency. Its energy is a resource that itself is traded. It's a commodity. It's not something that we just have guaranteed energy. I'm not going to get into my post-apocalyptic rant, but it's not always something that's going to be guaranteed. So if you can reduce the amount of power that is consumed, reduce the cost, and reduce the amount of power, your device is going to be a lot more feasible. Okay? If you have to completely shut down a power plant because you're consuming 100% of a power grid's power in order to run a device, which there are actually devices that have to basically have their own mini power plants just to power them. If you have to do that, there's a substantial cost there, and there's also a substantial potential for failure. The less power you consume, the less potential you have to make a mistake. Low power systems tend to be more effective systems. That's just the nature of it. The third step was talked about in the book was effectiveness. And a lot of this has to do with going back to the design constraints. Does it satisfy the constraints? And how well does it satisfy the constraints? If I give you a truth table, and most of the time your device will perfectly execute that truth table, but you have like a 0.5% chance that you're going to get a false reading out of your system. I mean, it is a problem. Every system is prone to fail. But when it comes to how are you going to make something work, you always have to anticipate the fact that your system isn't going to behave normally 100% of the time. Okay? Especially an electronic system. Electronic components themselves experience failure, and it's unpredictable. So you can't really predict that your system is going to fail unless you're buying like really, really cheap components that have 50% reliability, then you can pretty much guarantee it's going to fail. Better components tend to cost a lot more. So, yes. Now the fourth metric so this has to do with reliability, maintainability, availability. Is it going to perform well? Is it something that if it fails, are you going to be able to fix it? That system that I handed around, which by the way, this is the control motherboard for a treadmill. Anybody guess that? This is itself, this is probably 1990s technology. We have integrated chips that can do a lot of this. You'll see how many thousands of resistors are on here. For those of you who took 350, these are 6 MOSFETs. They're used for power switching. You have a couple of disk capacitors. I should probably hold this up with the camera to see. By the way, this is a printed circuit board on the back side. You can see these are basically all the wiring connections that go between these. They've been covered over with plastic, so you can't see them very well. But that's it. If that system were to fail, how easy would it be for you to fix it? If it comes down to, this system failed, all I have to do is replace this resistor, which is for some reason disconnected. All I have to do is replace this integrated chip. All I have to do is resolder that connection. If that's all it takes, great. Maintenance is awesome. But when you get into higher power systems, or when you get into really strong systems where if it fails, it lights on fire. I was doing some snowplow work over the weekend, and we managed to burn out a solenoid and that was used to power the hydraulics, which was awesome because your snowplow is useless when you can't lift the blade. Which is kind of a little bit backwards because you want the blade down, but at the same time you have to pick it up. We had to replace the solenoid in that snowplow in order to make the whole system work. And it experiences such high power that it doesn't just fail by like, oh, it doesn't work anymore. It fails by lighting on fire. And it did. It was kind of fun. Not so much fun trying to fix it or smelling it, because that was terrible. But that's... High power systems tend to fail in fire. Low power systems may tend to fail by broken connections, Simple, easily fixed. You may have a cracked resistor or a cracked IC. In that case, just replacing a component is fairly easy. But if you experience a fire, it may burn up your entire board. Maybe you have to replace the whole system. And that can be expensive, especially if you purchase that component from a company that no longer exists. Yeah, let's not go into that. Okay, well, also the book talks about performance. Okay, now performance is a huge aspect of electronics. Performance here this is your measures of quality. Okay, performance doesn't refer to does it solve the problem. Does it solve the problem is your effectiveness. This is your constraints and your functional requirements. Performance itself is related to your measures of quality because it's like, okay, how many of you in here use a 1990s era Windows 1995 computer as your main squeeze? Nobody. And I know that for a fact because I've seen most of your computers, if not all of them. Okay? Why aren't you using Windows 1995? Well, some of it's because it doesn't integrate with a lot of programs, today's world. Most of it comes down to the fact that Windows 1995, it was a great operating system at the time, but it doesn't have the power and it's not built for the kind of hardware that we have in today's world. Okay? It isn't able to execute commands as fast. It doesn't have the kind of clock speed. Clock speed has increased since 25 years ago, and it's increased substantially. We're now looking at gigahertz level systems where it is able to reliably oscillate between an on and off system. A clock signal, for those of you who may not know, it just goes on and off periodically. That's all it does. It's on, off, on, off, on, off. Okay? On your high end, I believe there are commercially available 2.4 gigahertz systems. Those systems tend to be really expensive. You get a megahertz system, those are cheap. If you get an operating system that runs off of megahertz, it will run slower, but it will also, those will be the computers you can drop kick and you won't feel bad about. But you can also get a clocking speed of seconds, where one clock cycle takes multiple seconds to run. And there are some benefits to having a system like this. Okay, we'll go back to talking about power. Now, cost and power themselves, these are also measures of quality. So this is measures of quality, this is measures of quality, this is constraints, functional requirements. If we reduce the clocking speed, you are always going to reduce the power. Because power is consumed every time a gate is switched. Gates only switch on the edges of the clock. That's it. So power is really only consumed on the edges of the clock. So the faster your clock is, the more power you're going to consume because you'll have more gates being switched per unit time. Okay? And that's what power is. Power is energy per time. So faster clock, more energy per time for the same number of gates. You lower the clocking speed, you will reduce the power substantially, and sometimes you don't need a process to be performed instantaneously. Sometimes you can have a computation that takes 60 seconds, 60 minutes. If you're doing still frames once a day, your clocking speed can be pretty slow. You're taking a measurement once a day. So all you want to know is once a day. You can have a clocking speed that goes into the minutes per cycle. It may take a minute to go between this peak and this peak. it's going to reduce your power substantially. If you've done any really in-depth research on IoT, which by the way is your homework for next week for the design problem, IoT systems require really low power consumptions. Oftentimes because they're put in remote situations. A lot of IoT systems will brag about the fact that they run off these little button batteries and they have a lifespan of 2 years before you have to replace them. Okay, IoT systems do require lower power, and you do have to reduce the clocking speed. You're not going to have a friggin' gaming computer out there used as an IoT device, because a gaming computer sacrifices power consumption for more performance. And also, when you're sacrificing performance, you can reduce the power, reduce the cost. That's what it is. So the beauty of developing IoT systems is that you're creating a low performance device. That's it. You're not creating a high-end, high-performance device. Now, you could build a high-performance device if you really wanted to. This class is intended to teach you kind of both ways. But an IoT system tends toward sacrificing performance for power and cost because the performance isn't needed. A lot of IoT systems, the way that they work is they will actually, it's almost as if, okay, so if you use the example of your cell phone. In your cell phone, how many of you guys have iPhones? Okay, iPhones have really championed the fact that they put in multiple cameras, and the multiple cameras allows for image clarity, image clarification, allows you to combine multiple images to come up with a single, fairly crisp image where you can distinguish foreground and background. Sometimes you can even take measurements with them. iPhone has done a lot of work with that, and Apple has. Now that type of a system is extraordinarily computationally heavy. Okay, that type of a system requires a lot of performance, which is why iPhones are needed to have the incredible processing power that they do. Need to be in the compact size that they do. It takes a pretty beefy processor. But to do that same system, it would be much more challenging if all it was just a camera. It's just a camera with feedback where camera system directly integrates with the screen. That's much cheaper. That's what the original iPhones, when they came out, that's what they were. It's just it takes a camera picture. It doesn't matter if it's low quality or not. It's just a picture. But with all the processing required, it takes a lot more computation to get one picture than ever before. Okay, and then you have pictures sizes that are 20 megapixel that are pretty standardized on a phone now. That's a different story. If we were to make this an IoT device, what you would actually be doing is you would be taking a picture and then you would be streaming that picture data to an off-source processor that does all of the calculations. So maybe the iPhone would take 3 pictures simultaneously, and it would stream all that data somewhere else, which would then process it, and it would then send back information. That reduces the performance required out of a device, which ultimately reduces the power and the cost of that device too. And that's kind of the idea behind IoT. It takes a snapshot, it'll take a measurement, but rather than sitting there and being like, okay, this measurement is, I'm looking at this trend, it's gone up 30%. No, that's not what it does. The goal of it is take a very simple measurement, send it to somebody else. That other person will receive that signal, process it, and then they may send a simple signal out to another IoT device that acts as an end effector. That may be something that turns on a motor. It may be something that closes a gate. It may be something that sends a red flag to an administrator somewhere. And that's really what an IoT system does. It's the performance is offloaded away from the device to something else. Okay? All right. So this is the foundations. I guess that's only 4. I thought there was 5. I'm pretty sure this mentioned 5, but I would need to go back through my notes and figure out what the 5th one is because I only have 4. Great. I can count to 5. I think. All right. So my goal for this class is I want to do a lecture like this once a week, and that's it. We'll talk about important stuff that's related to book material. I'm going to try to do that on Mondays. I was hoping to do this on Monday because I want to give you the rest of the week to work. I'm going to modify what we're doing for the rest of the week to accommodate the fact that, we didn't have school on Monday, which it's not going to hurt this class terribly much that we missed a day. I hope you all enjoyed a snow day and continuing quarantine. So I'm not going to give a lecture like this on Friday. I will try to reserve my lectures on Monday. If we get behind in course material, I may creep into Wednesdays for lecture days. But really, Wednesdays and Fridays, I want them to be more design. I want them to be soldering, putting components together. Been ordering components for us so that we can start building some circuits. At some point in the semester, I would actually like all of you to design PCBs, which is, it's this board. It just connects stuff together. You solder things to a PCB to connect them. If you had if you took 350 with me last semester, we had the little proto boards. Proto boards are like PCBs where you have to solder the wires yourself. PCBs, the wires are connected to the board, which makes it so much easier because then it's just plug and solder rather than plug, solder, check your connections, all those fun things that you have to do to make sure your wires aren't touching. All right, any questions about design here? And I'm trying to rush this. Again, everything comes down to you have to understand what your problem does. You have to understand how to know how well your problem is doing. And really it comes down to these 4 things when you're looking at how well a problem is solved by an electronic component. Now there are other design metrics. I mean, if you have a light integrated into your electronic circuit, then it's, measure quality is how much light output is and how reliable the light output is and what the frequency is and whether or not it's visible and whether or not it's adjustable and whether or not it's user-friendly. And I mean, there are tons of other measures of quality that go into these systems. It's not just these 4. But these 4 are extraordinarily critical for any electronic system because this is usually when you're going to buy a computer, brand new computer, you look at the cost, you look at how much processing power it has, you look at what the consumer reviews are of it and whether or not it's failed, and you look, the performance. How does it do? You may not be looking at power, but that doesn't matter. All right, on Friday, I will be again streaming a lecture through the interwebs. Just because that's what, unfortunately, we have to do because of the quarantine. But I will be streaming class, but we are going to be talking about your homework that's going to be assigned to you. I'll probably put it up on Canvas today, but we'll talk about it and work on it in class on Friday. All right. Also, I have a quiz I have to give you. Quiz is going to be kind of light. Quiz will be covering materials that was given to you in the textbook this week and given to you in the lecture that I just gave you. So that will be due Monday. I'm going to make it light because because I can. All right, any questions? Okay, I'll see you all Friday.